So we're going to do something that is kind of interesting in this case. What we're going to do, we have our PN junction. It's at equilibrium. We have this depletion width that occurs right here. And we're going to do something that we always do. We're going to apply a voltage. Okay. And in this case, we know what it looks like when there's no voltage applied. That gave us the junction voltage, the V0 that existed right there. And we also know that if we forward bias it like this, I'm going to apply a forward voltage. So if we look at this, we have that gap energy. This is going to be evenly level, and so I'm just going to draw all three of these on top of each other. Okay, this was V0. If I apply VF, we end up with something. This is going to drop and be V0 minus VF, forward voltage. If I apply a V reverse, which is going to be obviously in the opposite direction, let me do that in green. It's going to increase this junction. And just so we understand what happens here is as we do the forward bias case, and my colors are all off, but as we do the forward bias case, we end up shoving more electrons in here. We end up with more holes because we're drawing away the electrons out of here, and that ends up shrinking our depletion region, okay, to the point where we can easily kick across electrons and holes. We end up with a surplus of electrons and holes, and eventually they're going to be able to overcome that junction voltage and just go. Going the opposite way with the reverse bias, our depletion region gets wider. Okay, and so we end up with holes still over here, but we're shoving electrons in here, and they're annihilating each other, and it makes this gap bigger. We're pulling electrons out of here, which makes that region smaller. We're essentially applying a voltage against what exists there, and it just makes this gap bigger and bigger, and no electrons are flowing because it's harder and harder for those to get by from one side to the other. We're going to just very briefly look at the forward bias case, okay? And in the forward bias case, what we care about is what we call ID and IS. The current through it is equal to ID minus IS. ID is the diffusion current, and then the drift current is IS, okay? And so what's left over is the diffusion current increases substantially, and then we eventually get current I that goes through there. So that's all I'm going to say about it, is we can get to a point where ID minus IS is not zero. Okay, if we're in stasis, then it's zero. Otherwise, they're going to. If we are in reverse bias case, I think that's the much more interesting one, and this is going to look a lot like an equation that we had before. In fact, I'm going to forego writing it on the whiteboard, and we can go. Again, sorry, you guys are probably getting annoyed with that. And so if we go and look at our equations in the reverse bias case, this is exactly the equation that we had before, other than we do plus VR. So we have the forward voltage, VR, the junction voltage, and VR, the reverse biased voltage, that are applied to this. And the width is going to get wider. Yes, it will. Even the square root cannot squish this. So it squishes it a little bit, but not much. The junction charge also increases by the same factor. So if we go back to the previous equations, which are right here, The only difference is V0 and V0. Now it's VR and VR. And so that's all I'm going to say about it. There's a lot of equations that the book has. It talks about diffusion length. It talks about energy levels, the depletion region. I'm not going to go into those because it's just too in-depth for what we care about. The thing that we really care about is, well, depletion capacitance. And so I'm going to switch back over to the video. And what ends up happening is we end up with, if we were to plot the reverse voltage, okay, VR versus the junction charge, okay, we would end up with a curve that kind of looks like this. It's a square root, right? So that's the equation that we just had, which is QJ is equal to A times the root V0 plus VR. There we have an offset, so if VR is 0, we still have some junction charge that's built up there, okay? But then it keeps on going up in this direction, okay? And then we're going to just pick a point. Let's say we junction it. We have a DC bias voltage that we're putting through it or onto it that's right there. This becomes our bias point. And if we just draw a tangential line there, the slope of that is our junction capacitance. So whether we want to or not, diodes have junction capacitance. And that can cause problems. The junction capacitance is probably the biggest difference between a power diode and a signal diode. And look at this. One of the biggest things that we have with this, one of the scales for this, is A. What are the things that we can do with our diodes again? The things that we can control, A and D. That's it. And so that A ends up being a big factor on what the slope of this is, because it can affect this entire area of the curve. So what does this look like equation-wise? Well, the charge, the junction capacitance, is equal to D by dQj, the derivative of the junction, with respect to the voltage, the reverse bias voltage, for given that VR is equal to VQ. Okay? So we could go through a lot more math on this. It doesn't sound like very much fun. Instead, we're just going to give you two equations, and I'll go back over to the other board, to the written out nicely equations. Somebody did the math for us. Cross-sectional area comes in, so bigger cross-sectional area, bigger the junction capacitance. And so you can do that with that's how we design bigger, more current ability, but more capacitive diodes. Epsilon of silicon comes back up again, multiplied by Q divided by 2, Na times Nd now, over Na plus Nd. And this is multiplied by 1 over V0. Okay? So that's our entire junction. This is junction at 0. So in other words, there's no reverse bias voltage applied to this. Okay? And so what we want to be able to do, though, is just so we can use this equation. This is going to be a constant. And kind of the nice part about this is if we reverse bias it, the junction capacitance changes, but we'll use this value that we just came up with, Cj0 over 1 plus VR over V0 to the M. M has to be given to you. VR is our reverse bias voltage. V0 is our junction voltage that we'll have to calculate. and CG0 we calculated from this. But this allows us, if we apply different reverse biases, it gives us different capacitances. The reason why this is so important is one of two things. If you have diodes in your circuit, they're going to cause capacitances. And so first of all, before I get to that, and I just did it again, get annoyed. Okay. My sound engineer, sound engineer is me. Okay, so coming back here and looking at our equations. Depletion capacitance. This is the end of the equations. I've gotten to the end of the sheet for this. Cj is equal to the derivative of the charge divided by derivative of the charge with respect to Vr. Given Vr is equal to Vq, and then we have the entire junction capacitance if there's no reverse bias, and then we do this. So the value of M, by the way, can vary depending. It's usually from 1/3 to 1/2. It would make a lot of sense if it were 1/2 considering the equation that's right above it. But it can vary just a little bit. It's called the grading coefficient. So we're going to go back to playing with capacitance. And there's a reason why this is important. So if I have first of all, even in forward bias, there's a little bit of resistance or a little bit of capacitance. And if we just model this for forward bias as a capacitor and a resistor, what do we have? A high pass filter. Okay? If this is our V out, excuse me, V out of T, this is a high pass filter. Okay? So something to think about. That's really weird. And something that we need to worry about. In reverse bias, okay, this is going to look like an open circuit. Okay? So we're going to say it looks like an open, but really, so forward bias isn't quite as bad. So forward bias, we have this capacitor, and it's junctioned with like a voltage source. Let me draw this. Forward bias, we're going to replace this with this 0.7 volt, and there's a capacitor in parallel. That's not so bad. Okay? That's what we're going to replace it with. In reverse bias, we have an open circuit coupled with a capacitor, and that's where it does become a high pass filter. So if you have a negative DC that's going through this, or just multiple frequencies, it's possible that you're going to get high frequency junk coming through here because of that capacitance. It's not just going to block it. We're going to get high frequency junk that's going to come through this value. So it's something to be aware of that it's there. Okay? Or we can use it to our advantage. Some people, this is the varactor diode that we caught on the very end of that chapter. We could put this here, have an AC signal, have a DC source. It comes through here. And now we have a variable capacitor. But it's only variable on the AC. And so if we look at the AC waveform as it comes through here, and then vary this, the capacitance will go up and down, changing the corner frequency of our filter. And so this is called a varactor. We intentionally can make these, and then like I said, whether we like it or not, there's always going to be some capacitance across diodes. To finish off this lecture, I just want to point out maybe a cool circuit of the day. If you have if I have a voltage regulator over here, V in, V out, and this, so this is like 5 volts, and I have a 10-volt source over here. If I hit this with negative voltage, it's possible that it could blow up. Okay, and so one thing that we can do, so you could hook this up backwards. I'm going to show you backwards. Okay, it blows up. Instead of getting 5 volts out, the thing freaks out, and the magic smoke comes out, never to appear. And so what you can do with this, what I would do, and what I've done, is I just put a power diode in series. And now what happens is this is going to reverse bias. It's going to, right now it's going to reverse bias. No current's going to go into this. No smoke is going to come out. If I hook this up properly, current's going to go through this. We're going to put this over here, and just what I would do over here, I'm going to use another LED, another diode. Going to have an LED over here that indicates that sure enough it did get powered on. And so that way the smoke doesn't come out. So really simple, one diode protection circuit. Make sure that the current only goes one way.